Okay, so O by lambda here. Identity 9. Well, Landau's theorem. F of S is analytic in sigma greater than -1. And if sigma naught is now less than or equal to -1. That means it's the Dirichlet series is valid up to -1. This is the key point in Ingham's proof. So this simple fact about the Riemann zeta function having no zeros here was useful. Because otherwise, I cannot bridge the gap between here and there. Even though it is simple, that permitted me to travel too. All right, but now we'll get a contradiction. So observe that. From the right-hand side of 9, f of 1/2 is 0. Because f of 1/2 is zeta 1 at the bottom. And the Riemann zeta function has a pole. This is simply the Riemann zeta function at half, squared, whatever that value is, etc. Therefore, f of 1/2 is 0. But from the left-hand side of 9, we have f of 1/2 is greater than or equal to 1, because this is a Dirichlet series with non-negative coefficients which you have said converges. And the very first term of the Dirichlet series is 1, and all other coefficients are non-negative when I put s equal to half. So the left-hand side is at least 1, and the right-hand side is 0. Contradiction. Really, it's a lovely proof. The contradiction arose out of this assumption. Suppose. Hence, zeta 1 plus AMI, this cannot be 0. But A is arbitrary. That's 0. Really lovely proof. I mean, if you see all these simple results that we have proved are all coming together. So this is Ingham's proof of Ramanujan's theorem. So Ramanujan's presence in England really was very influential, and in many ways also stimulated a lot of fantastic mathematics in England, of course, because of Hardy. And Hardy and Littlewood, of course, were the leaders of the British School of Analytic Number Theory. A lot of these people were either students from Hardy and Littlewood. Littlewood actually had PhD students, or they had these people as strong influences. And so when you hear Montgomery or Bob Vaughan or Heath Brown and all these people, they're all coming from this wonderful tradition of set up by Hardy and Littlewood. Okay, so that's that. Now I'm going to give you your homework assignment, and we'll discuss the problems a little bit. It's on both sides. One more thing. And I will tell you why I chose some of these problems. So they're all related to everything we have done here. And I'm hoping to cover as much as possible of what I have done.
We've got one that's one-sided on both.
Oh, then I gave you the wrong number.
Probably the original.
Yeah, I gave you, this yours, both sides?
Yeah.
I think I gave you, okay. I gave you, so that's supposed to be.
And I gave it.
Oh, you also?
Yeah.
Okay, you also got that. All right, so problem 1. I mean, it's a simple one, but it's kind of interesting because the harmonic series goes by steps of 1 over k. And these steps are very, very small. So what this problem says is, no matter how small these steps are, it never hits an integer value beyond 1. I have said hint use Bertrand's postulate, but I'll give extra credit if you do not take my hint and give another proof. It's okay. So, but I just said it's a nice application of Bertrand's postulate here. I don't want to say too much about number 2. These are just some clever inequalities that you have to use for divisors, and you'll get both the harmonic mean and the arithmetic mean statements. Problem 3 is actually quite interesting. There are many proofs one can give. I was actually able to think of it in terms of partitions, but that's because 1/2 of my life has been as a partition theorist, so I like to connect analytic number theory with partitions. But a more or less routine proof can be given using Dirichlet series. So here's what it is. You sum -1 to the n over d times d. Now the point is this. -1 to the n over d is not a multiplicative function. N over d is multiplicative, but not -1 to the n over d. But you can still think of it as a convolution. A function evaluated at n over d and a function evaluated at d. So that's why I said use Dirichlet series to calculate the generating function, and then you'll end up with the sum of the odd divisors of n. So this sigma naught is not the sigma naught used here, nor is it sigma a with a equal to 0. It is the sum of the odd divisors.
Sigma is O.
It's O. Yeah, so I should have put O instead of 0. Sigma O. Okay. Now, I like number 4 because I think of it as the multiplicative version of the well-known identity that the sum of the cubes of the first n natural numbers is the square of the sum of the first n natural numbers. So it's sort of that, a version of that. Okay, so tau is the number of divisors then, not there are numbers in tau. Okay, number 5 is pretty routine. It's just one better approximation than what we got. Okay, but what we're doing here is we are introducing this function. Sometimes the function is called the onion. Like onion has got several layers. Okay, so this is the onion upon the 2. So the average value of the fractional part of x is 1/2, right? Because the fractional part of x goes from 0 to 1. So I'm subtracting off the average value, but when I do that, I get a function which is both positive and negative. It's the sawtooth function but moved down. But it's equally often positive and negative. So that's the property you got to use. That when you take the area of this function, you'll get always a bounded area because the negatives will count positive and negatives off. So you establish this quantity which involves this onion, and then use that property to show that that integral is no more than 1 over x squared in size. So this is a very sharp approximation to the harmonic sum with the Euler constant and this. But now once you have done that, you can use that to get a very nice expression for the error term in the Dirichlet divisor problem. Remember I told you about the Dirichlet divisor problem. We proved that the sum of tau of n is x log x plus 2 gamma minus 1 of x plus capital of square root of x. And I said that the Dirichlet divisor problem is to the famous problem. We didn't work on that problem here in class, but it is to decrease that x to the 1/2. That Hardy showed you can't do better than x to the 1/4, and then Voronoi had shown x to the 1/3, and then one of my acquaintances at UCLA was the ultimate champion, and then he went on sculpting and so on, Gregory Kolesnik. Now, look at this expression in number 6. Apart from the constant -2, we are writing this as the sum of this onion function at x over n, but only up to square root of x. Now, this function can be negative and positive, so there is some cancellation there. So, if you think of this onion of x over n as some sort of random walk, negative and positive and so on. In a random walk, after a certain number of steps, the distance that you expect will be square root. So, this onion of x is maximum 1/2 on one side and minus 1/2 on the other, and you would expect this to be some sort of randomness here, I don't know. So, x to the 1/4 is sort of hinted by that. You're not proving Dirichlet divisor problem. I'm just asking you to establish this representation. This is perhaps the hardest problem in this whole list because it involves some detailed calculations. But it's only calculations. It's not, no brilliant idea is needed. You got to go through the Abel summation formula very carefully. Pay attention to every little thing that you see on the way. Every little pebble is important. Okay. Now, this problem is quite interesting. So, in class, I did this Mohan-Nair proof, right? Psi of x with x to the n, 1 minus x to the n. Did I do that here? So, likewise, we use this other polynomial, x squared, 1 minus x whole squared, 2x minus 1. Compute the maximum of this. That's a calculus problem. But then, look at this particular integral, and using that integral and the fact that the same idea that goes behind x to the 1 minus x to the n, you can get a lower bound for psi of x. And this is a little bit better than the lower bound you get with x1 minus x. So let me give you a little bit of the history of this problem. So when I was in Ann Arbor, Michigan, we heard this news about this young Indian student, Mohan Nair, in Glasgow, a student of Robert Rankin, who got this lovely proof of x to the n 1 minus x to the n thing from psi of x. So Montgomery got quite excited by this. And we had at that time a visitor from Australia by name John Mack. So he came spending his sabbatical to work with Montgomery. So Montgomery said, why not we work on this? And instead of x1 minus x, let's look at some other polynomials and see whether we can get better bounds. And they were able to obtain actually an infinite sequence of polynomials, and the bounds kept increasing. Now, if one was able to get that lower bound to be 1, or 1 minus epsilon, one would be able to get a proof of the prime number theorem by this process. But unfortunately, the sequence of polynomials that Montgomery and Mack constructed, when they computed the limits, they all went on increasing, but they stopped less than 1. It converged to some value less than 1. I think for this reason, Montgomery didn't publish his work, even though it was lovely, the construction of these polynomials was quite elegant, but he didn't publish it. But I think also a Spanish mathematician had done some work. But anyway, this is an interesting thing. So I took this from Nimon and Zuckerman as revised by Montgomery. So that's where the source is, going back to 1980-81 when I observed Montgomery lecturing on this. Number 8 is something I mentioned before. So if you look at log p over p and subtract log x, and if that difference converges to a constant c, you can show, if you assume that fact actually implies the prime number theorem. So this would be another way to prove the prime number theorem. So that's why that problem is important. Go through the Arwell summation, but carefully, you'll get it. This was a fact that we used, so I gave it as a homework, but I've given you a hint. The largest prime power divisor of a number goes to infinity. The largest prime divisor does not go to infinity, right? Because you can have a number like 2 to the alpha, 3 to the beta, then alpha and beta go to infinity, so n goes to infinity, but the prime divisors are just 2 and 3. But the largest prime power divisor always has to go to infinity. Okay. Now this is an interesting problem, 10. Somewhat artificially constructed, perhaps. Okay, but the problem is given to convey a point. You have a Dirichlet series defined by a multiplicative function, and therefore the Dirichlet series enjoys a product representation. From the product, you can calculate zeros from the convergent product. You can calculate zeros of this function by just saying when the factors vanish. Do this calculation, and then you'll be able to show that these zeros will have some sort of a limit or cluster point, and that will destroy the analyticity on the boundary. So it's not a difficult thing. Next, I want you to use the outrageous method of Ramanujan, not by rigorous methods. I want you to use the hand-waving outrageous method of Ramanujan to show zeta minus 2 is 0. So you learn something from it. That means 1 squared plus 2 squared plus 3 squared is equal to 0. And after you have done that, I'm sure you will show it to your cousins and various people and get them to sort of wide-eyed look at what you've done. This is a simple but interesting fact that when you do the Laurent expansion of the Riemann zeta function, we know the first term, 1 over s minus 1, because we know what the pole is, simple pole. But the simple question is, what is the first constant that we get? And it turns out to be Euler's gamma. Okay. Follow the proof of summation mu of n over n is 0. We already encountered summation mu n log n is little o of n x log x in our proof. But here I'm asking you to show that that series converges to minus 1. And the last problem is, there is nothing very special about that particular cosine polynomial, trigonometric polynomial that de la Valle Poisson used. There are other trigonometric polynomials also that can be used. So here's an example of one other trigonometric polynomial. 5 plus 8 cosine theta plus 4 cosine 2 theta plus cosine 3 theta. And that turns out, just verify, imagine that you're back in your pre-calculus, check that it is greater than or equal to 0. Once you have done that, you can prove, you can get this inequality for the Riemann zeta function. And once you have that, get a contradiction if you assume zeta 1 plus it is not equal to 0. So this is exactly like the Dalla-Valle cosine proof. So one can use other polynomials, but this polynomial has no superiority over the earlier one. In fact, it's more complicated than the earlier one. So Dalla-Valle cosine is among the simplest of the polynomials. Nevertheless, this gives you some sort of a flavor of many things we have done, and it ties together a lot of things we have seen. All right. Yes.
It says it's due November 11th, and that's Veterans Day.
I'll give it to me. Is November 11th on Veterans Day?
Yeah,
Okay. Enjoy the Veterans Day, usually Monday.
on the 14th.
One more of this, oh my God, I'm not worried about this class, I'm worried about the next one. Every class I lose, Monday, Wednesday, Friday, it's a big thing for me because I'm covering material for the differential equations and I want to do some stuff